Hello again, folks, in 113. Today we're going to be covering section 11.5, which is very close to the end. And that section is called compound probability. Just a quick look at the calendar. Okay. Today is Tuesday, December 7th. It's my cousin Susie's birthday, and also infamously Pearl Harbor Day. 11.5 is our section. Let's see, the packet that I have for you consists of this overview diagram. So I would actually strongly, it's a little bit complicated, but we're going to go through it. I would strongly encourage you to print this because it summarizes the formulas. If you feel more comfortable, here are the same information swiped from the textbook and uploaded as PDFs, and it has definitions, and then there are the actual examples that we'll go through. Okay, so if you're following along, you can print that out and annotate as necessary. Let me turn this on. Let me just scoot this over just a wee bit here. Lighten me a little bit. Okay. I have to adjust the light behind my board. I will. Let me get rid of this for a moment. Pull up that instead. Okay. So as I mentioned, we're in chapter 11. This is where we have been to this point. This is where we are. This is where we're going to go. Compound probability is the subject for today. Alright, let me show you that overview again. You may remember from a while ago I was saying that I don't want to dig for it on my computer, but there are, I think I better do that, okay. There are, probably an infinite number of probability experiments you could perform, but there tends to be, in the discussion, 3 specifically. So I think I had made a diagram. Here it is. A while ago. Right. Coin flips, die rolls, and card draws. Right. And the earlier material, the coin flip came up and the die roll came up a lot, and they probably will still, but when we get into this conditional probability, that eventually too, but the compound probabilities, card draws are the probability experiments that are analogous or easily translated. So you'll see that a lot. Anyhow, it is often inconvenient to try to draw a tree diagram to determine the complete sample space of 2 consecutive events. For example, if you were going to draw a card, draw 2 cards, with replacement, according to the counting principle, we could employ this simple formula. Right? The number of outcomes possible for the first times the number of outcomes possible for the second. So if we're talking about a standard deck of playing cards, there's 52 cards in the deck. Right. That would end up meaning that there are going to be 52 times 52, which I want to say is 2,704 total sample points. Right. For lack of a better phrase, because I don't want to get in trouble, that means if you're drawing two cards, let's call them combos. Right? Not really using any formal definition there. Right? Combos of two. Right? 2,704 of them. Right? So that would be quite a tedious tree diagram to have to draw. Right? Counting principle is great, at least in this respect, that you can determine the number that there would be, so you could avoid that, avoid drawing. But the point of this section, compound probability, is that we should probably take the terms or and the word and into consideration, because that will decide whether we're going to use these formulas here or these formulas here. Okay? Anyhow, for compound probability, playing cards help illustrate these concepts. Now, when you see the word or in context, all right, this is indicative of the addition set of rules, which are basically these two formulas. All right. Insofar as an operation is concerned, it's going to be addition. All right. All right. But what you have to decide is whether the situation described is mutually exclusive or not mutually exclusive. Let me zoom in just a wee bit here. We'll keep our focus over here, the addition rules. Okay. What does it mean to be mutually exclusive? It means that two events cannot occur simultaneously. Okay. Right. And in that case, here is the incarnation of the probability formula that you want to employ. All right. You might write it as the probability of event A or B is equal to the probability of A plus the probability of B. Right? And an example of that would be the probability of drawing an ace or a queen, right, out of a deck of cards. Not to belabor the point, but yeah, I'll take these out again just for visual aid. As you can see, right, and this is just one queen as an example. An ace and a queen are two different cards, right? So they cannot be the same thing simultaneously, right? They could be the same suit simultaneously, but the whole card they cannot. Right. So this is the appropriate formula, right? If you're going to calculate that, I'll do it real quick. In the case down here, I'll just sort of superimpose it if I can help it. Just pay attention to what is in green here. The probability of drawing an ace in a standard deck of playing cards is 4 out of 52. Right? The probability of drawing a queen in a standard deck of, a poker deck of playing cards is also 4 out of 52. Right? These are the same denominators, so in terms of the legalese of math, you can add those immediately, just basically add the tops. And you would have 8 out of 52, which you can simplify, of course, by dividing by 4. And then you would end up with 2 out of 13. Right? In terms of a percentage, which I think is a little bit more warm and fuzzy, it's about 15%. 2 divided by 13 times 10, times 100, and then rounded. Right? So the probability of drawing an ace or a queen would be 2 out of 13 roughly, or about 15%. Okay. Now as an example of what is not mutually exclusive, these are things that can occur simultaneously. You have to be aware, English is often the culprit for confusion, right? Can is associated with this concept of not mutually exclusive, all right, rather than cannot, all right? So just be aware, all right? If it's not mutually exclusive, then it can occur simultaneously. I guess that would be a double negative, right? In terms of grammar, right? An example of a situation where things can occur simultaneously would be the probability of drawing a heart or a face card. Right? Now again, just to flash this really quickly, if you had a heart, it's like a Tin Man, right? There are 3 face cards that happen to be hearts. So these things can in fact be one and the same. All right, and because they are one and the same, they are possible as one and the same. All right, we would call them not mutually exclusive. All right? And the appropriate English word to use would be "and" in this case. Right? It's still an addition rule. All right, but we're going to use a slightly more complicated formula. The probability now, let me not double talk here, but let me zoom out just a wee bit to show you something. These are still the so-called OR addition rules. But notice something. We're going to start with this. The probability of A or B, that is the first thing, first game, or the first event, and B is the second one, is equal to exactly what we had here. Probability of the first plus the probability of the second. But because we don't want to count something more than once inadvertently, there is an extra chunk of this formula here which incorporates the word "and," right? The probability of the thing that is both A and B simultaneously. Okay? To add some distinction from this "and" over here, I just put that in lowercase, right? I hate the subtlety of that, but I don't want it to conflate one with the other. Right? So these are things that are not mutually exclusive. Right? The situation for card draws that are not mutually exclusive is probability of the first plus probability of the second, subtracting out that situation where they do occur as one and the same. Right? So to illustrate, we'll do that example that you see in red here. The probability of drawing a heart or a face. Yeah, I was able to find some sort of icon to simulate. The probability of drawing a heart or a face is equal to the probability of hearts. There are 12, is it 12? There are 13 hearts out of 52, right? And the number of face cards, well, there's 3 hearts, 3 spades, 3 clubs, and 3 diamonds. So there would be 12 out of 52 in that instance. And then there's the things that are both of those at once. So the simultaneous cards that are hearts and faces. And there are, in this subtraction, 3 out of 52, right? Now again, when you're adding or subtracting fractions, remember that the denominators have to match, and they do. All right? We don't have to reinvent the wheel, and I don't want to sidetrack, but if you need to, employ this button here, ABC, so you can input fractions with the denominator as they start, and then it will give you the simplified answer. Right? So for example, if you had 13, you'd press 13 and then ABC, and this is the way it illustrates it on this type of a screen. Right, and as it's simplified as a quarter, because that's what it is. right? And you could add, the next fraction or subtract the next fraction, whatever you need to. Anyhow, follow the order of operations, just sticking with one side here. 13 plus 12 is 25. And 25 minus 3 is 22. So if this is 22 out of 52, it would be good to simplify by divisibility in this case. 22 divided by 2 is 11, and 52 divided by 2 is 26. So 11 out of 26, right, which 13 would be exactly a half, so it's just shy of that. Right? Let's see, what's 11 divided by 26? Right, about 42%. Just to make it a little bit, maybe intuitive. Right. Do remember, try to simplify it. If you're using a calculator, it will probably do it for you automatically. Right. Right. Anyhow, the point of this, let me back up now, is again, as you're going through your problems, in section 11.5 is that you're going to take into account you have 4 formulas for this section that are either going to be or type of problems, i.e. the addition rule problems, or you're going to have and, concrete capital letter and. These will be multiplication problems. Right? We've just discussed these so far. You have to decide for yourself whether the situation described are mutually exclusive or not mutually exclusive, because it does matter. That will decide ultimately whether you're going to subtract as an extra term or not. Right? So be very careful. Right? What's the difference? Right? Things that are mutually exclusive cannot occur simultaneously. They cannot be one and the same. What on earth is that? Someone is calling me from Illinois. I don't know that number. Things that are not mutually exclusive can occur simultaneously. And because they can, you don't want to count something more than once. Go away. All right, so we have to subtract off that extra term, okay? All right, now shifting over to this side of the board, we'll discuss the N type of multiplication rule problems, i.e. the multiplication formulas. Right, which, as you can guess, involves multiplication somehow, maybe. I'll zoom in on this. Okay. I made some special note here. Right, capital letters and here, and in the context of consecutive events. Right, English again, we have to specify a lot because there are words that may, descriptions that may get conflated. Seemingly similar things being combined and thought of as being the same. All right. The multiplication rules are for when events are either dependent or independent. What does it mean to be dependent? It means that the second event is affected by the first, essentially. Independent means one has no bearing on the other. Usually the visual cue that you're dealing with dependent versus independent is this phrase, or that one, without replacement or with replacement. All right, so train yourself to look for those. All right, and here are the formulae. Okay, so the probability of A and B would be the probability of A times, this is a multiplication dot here, the probability of B given A occurred. That is a verbose way of writing in shorthand, right? but you kind of need to do that. A lot of times in a book, they'll just simply write B given A, and they'll cut it off at that point. I like to be, as explicit and clear, hopefully, as possible. So I wrote it out like that. Probability of the first thing times the probability of the second thing given A occurred, because the second is affected by the first, somehow. All right. Over here for the independent, you'll see the probability of A and B is the probability of A times the probability of B, and then you don't have to worry about it any more complicated than that. Right? So here's two examples to illustrate these. Right. The probability of drawing an ace and then a queen without replacements, meaning you don't put the card back after you've taken it out. Right, so when we're figuring out the probability fractions to multiply here and here, we have to take that into consideration. We have to say, well, you've eliminated one of the total choices in the deck. So let's do this first, all right? And the sequence in which these things are described is very important. So if they talk about aces first, all right, then you be careful, all right? The probability of drawing an ace, there are 4 out of 52, right? Now, if you draw a card and then you don't put it back, right? When you get to this part of it, right, the probability of drawing a queen given an ace has already occurred, that is without replacement. There's still going to be 4 queens, right? But how many total cards are there now? Right? There's no longer 52. So that means that you have 51, right, when you multiply, right? Remember the basics of fractions, right? When you're multiplying fractions, you don't care if the denominators match. You can just multiply the top times the top, the bottom times the bottom, the numerators by the numerators, denominators by denominators at will. But it would be more strategic if you were doing this by hand to simplify first. Right? Now, whether you do that or you use your calculator is fine. I'm going to try to save myself a little bit of trouble here. 4 and 52, I could cross simplify. That's 1, and that's 13. And that's still kind of yucky. So it would be 4 times 13 over 51. Alright, I'm going to bite the bullet here and just use my calculator. This is not being any more efficient, really. 4 times 4 is 16, of course. 52 times 51 is 2652, which is a terrible figure. So up here I'm going to write 16 over 2652. Yeah. Okay. Now that is correct, but it's quite cumbersome. So let me show you an advantage again to using a calculator in a situation like this. If you figured out what the fraction should look like, then it would be these figures here, right? If you went to 16 and then ABC button here, at least if you have this model of calculator, and you should, then you went to 2652, it will simplify for you. Right. So you have that. Still terrible, right? But it's something. So you would end up with 4 over 663. Yep. Which again, if you want to make it perhaps a little bit more palatable to the general audience, myself included, convert that to a decimal percentage. And you get something like 0.6%. It's very tiny. Right. The simplest form of the fraction is usually preferred. So that's that. All right, now let's do one more example, and then we'll get to the textbook's examples. Okay. A person who called me, they left a voicemail, so advertisement, I think. Okay. And he thinks for this independent example, the probability of drawing an ace and then a queen with replacement, right? It's a very subtle thing, right? Change, all right? The probability of the first thing times the probability of the second. So it would be for the ace still 4 out of 52. But if you put the card back, now you're talking about things from the perspective of queens, it's still going to be 4 out of 52 because you put the card back. So in that instance, what are you going to get? You'll still get 4 times 4 is 6. Well, you know what? In this one, this would be to my advantage to simplify this one, right? 1, 13, 1, 13. 1 times 1 is 1, 13 times 13 is 169. So this would be 1 over 169 simplified. And that divided by 169 is almost exactly the same because it's so slight. And this would be rounding up. If you see in this instance here, I'll show you on the screen, a pi. 1 divided by 169. Here you have 0.0059 times 100 would move the decimal place to here, so it's not quite a whole percentage. It's 0.59. If you rounded it, it would be 0.6 again, approximately. Anyhow, the simplest form of the fractions is preferred. Right? I just do the percentages for my own sake because I think it makes things a little bit more intuitive. Yeah. Now, that's the whole kit and caboodle in terms of formulas that you will employ for section 11.5. All right. Just again, not to be annoying, but to be thorough. All right. You're going to have addition rules, which you could collect if you recognize that there's an or involved here. You'll have to take into consideration things that are either mutually exclusive or not mutually exclusive, because again, that affects the formula of choice. Right? Then there are the multiplication rules, which usually alternatively referred to by their and. Right? And this has to be, you'll distinguish between dependent and independent events. Okay? And then there would be these formulas, right, here and here respectively. All right, now let's try some of the textbook problems. Okay, here's the situation as described. Okay, if you can't see, I'm going to assume that for those of you who are watching this, you have this printed, but I'll read it to you. All right, each of the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 is written on a separate piece of paper. Right? The 10 pieces of paper are then placed into a hat, and one piece is randomly selected, so it's a random draw. Okay. Determine the probability that the piece of paper selected contains an even, this is fading, or a number greater than 6. Right? Now again, especially in the position of teacher, right? Do not be afraid to take what is given to you in context and reduce it to its bare essential. Boil it down to the essential, because sometimes things are just not written clearly, unintentionally, and then often they are written unclearly, intentionally. Right? So if you're going to teach this, especially to little kids, right, you want to make things as lucid as possible. So do the work for them, right, and then teach them the technique of how you got there. All right. Anyhow, so we're talking about a card. I'm going to write this in black because it'll probably be a little easy to see. To reiterate this, it is essentially a question of, right, what is the probability of an even or a number greater than 6? All right, now we have to decide, since there's this phrase of or here, which of the addition rules that we're going to be employing, those for when they are mutually exclusive or not mutually exclusive, right? The question is, right, can a slip of paper that is a number, in this case, can a number drawn be both greater than 6 and an even? And if it helps, draw out the entire set and then analyze those things specifically. All right. If it helps, here's the visual aid. Right. We're going to put this in set notation. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 in fancy braces for set notation, right? Roster style. Right. Well, let's analyze the things that are greater than 6 here. Right. So our attention would begin here. Right. Things greater than 6 are 7, 8, 9, and 10 logically, right? Are any of those evens? 8 is an even, and so is a 10, right? So can they be both at the same time? Yes, can be both. Which means they're not mutually exclusive. Not mutually exclusive. All right. And in that instance, if they're not mutually exclusive, then we have to employ this formula. The instance in which we're going to subtract out the things where they are the same, one and the same. So we don't count them more than once, unnecessarily. As long as there's sufficient amount of space, let me continue with this. I mean, you could get to the answer just using what you have here. But let's use the formula, all right? The probability of an even or a number greater than 6 would be, according to the formula model, the probability of an even by itself plus, because it's addition rules, right, the probability of a number greater than 6, and then since we're dealing with things that are not mutually exclusive, because they can occur both one and the same, we're going to subtract out the situation where we talk about the probability of something that is even and greater than 6. Sorry, I have a cold. Alright, so let's figure out what is the probability of the evens just unto themselves. This is an even, that's an even, that's an even, an even and an even. So there's 1, 2, 3, 4, 5. Right? So that means for this fraction it would be 5 out of 10 things, right? It's kind of a sloppy 5, but hey. All right, now, what are the probability of things that happen to be just generally larger than 6? That's larger than 6, so is this, so is this, so is this. So that would be 4 out of 10. And then we're going to subtract off the that portion of it that is even and greater than 6, which is just these two, right? So 8 and 10 are in the overlap. So that's 2 out of 10. Now, as you're following along here, remember, you have to use the correct order of operations. So you add first, the addition rules, right? And then subtract out 2. So, well, if the denominator is a 10, you don't have to worry about upgrading to a common denominator. 5 plus 4 is 9 out of 10. And then you subtract off 2, minus 2, and you end up with 7 out of 10, or 70%. Okay? So not too bad. The hard part, I would argue, is deciding whether things are mutually exclusive or not, because the phrasing of that in English is a little confusing. I hope I'm not speaking too softly, but I can't really raise my voice. Sorry. Right. Let's take a look at number 2 here. Okay. Okay, for example 2, it's still using the addition formulas, so let's guessing. Right. Consider the same sample space, the numbers 1 through 10, as in example 1. Okay, so we still have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And what are those? 9. If one piece of paper is selected, determine the probability that it contains a number less than 5, to abbreviate, or a number greater than 8. Okay. All right, so to just sort of translate this into the formula, remember to ask yourself, right, are these mutually exclusive? Right, in other words, can a number be both less than 5 and greater than 8 at the same time? So, are these mutually exclusive or not mutually exclusive? Can a number be both less than 5 and greater than 8 at the same time? That would seem kind of silly if you actually dwell upon it, right? A number cannot be less than 5, which would be everything from here to here, and simultaneously greater than 8, which would be from here to here. Right. So, can they be both? No. So then they are mutually exclusive. If they are mutually exclusive, and they would have to be, right, of these two addition formulas, we're going to go with the less complicated one. Right, so namely what is in green here. Sorry for the flashing lights. Okay. So, to translate this again into the formula, the probability of a number less than 5 or a number greater than 8 would be equal to the probability of the number less than 5 plus the probability of the number greater than 8. So it's just one fraction added to another fraction ultimately. Of things that are numbers less than 5, there are 1, 2, 3, 4. Okay. So that's 4 out of 10. And for things that are greater than 8, it's just 2 things. So 2 out of 10. And if you add them, it would logically be 6 out of 10. Sorry to write it up here. Which is 3/5, or you could say 60%, right? 3 out of 5, 3/5. Okay. Take a look at number 3. Okay. There's a lot to it here. One card is selected from a standard deck of playing cards. Determine whether the following pairs of events are mutually exclusive, and determine the probability of P or B. First thing, second thing. Okay. I guess technically you don't want you to do the other one, but it's silly. You can have to calculate the probabilities in either event, but you have to. The point of this exercise is to, familiarize yourself with mutual exclusivity. All right. Now, let's be clear about these instructions here. It's one card. All right. A standard deck. All right, and we need to know whether they're mutually exclusive or not. Okay. The probability of an ace or a 9. All right. I would argue that that is definitely mutually exclusive. And that's correct. I'm going to go through this and then we'll do the formulas for each of them. Can't be the same, right? They can't occur simultaneously. All right, card cannot be an ace and a 9 because an ace is a 1. It's like saying, can a 1 be a 9? It's not possible. How about this one? The probability of an ace and a heart. Can they occur simultaneously? Yes, they can. These are not mutually exclusive. Right. They can occur simultaneously. Okay. A red card and a black card is for sure mutually exclusive. Can't be both red and black simultaneously in card world. All right. A picture card, or a face if you like, and a red card. These are not mutually exclusive. These can occur simultaneously. A card can be both a face and a red card. In many instances, right? Okay. So, A and C, being that they are mutually exclusive, is going to be the simpler formula. So, for A, let me see if I can get myself some space here. Right. A and C are both going to be derivatives of this. A or B is equal to the probability of A plus the probability of B. And the others, B and D, are going to be not mutually exclusive, so they'll have the extra term tucked into them. So this is going to be the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. I'm just using that little symbol for and in this context here. Okay. I'll get out of the way in a second. Okay. So to get through this, let's see. An ace, I don't have to change the letter here, right? The probability of drawing an ace is 4 out of 52 if it's a regular deck, right? The probability of drawing a 9 is similarly 4 out of 52. So that's 8 out of 52. Simplify, divide by 4 is 2 out of 13. Similar to what we had done earlier in the examples. For B, with the probability of an ace, I'm not going to change that one. Right. The probability of a heart, a black heart, here we go, is probability of aces is still 4 out of 52. Probability of hearts is 13 out of 52. Because ace through king is 13 cards. And for those things that are both an ace and a heart, it's just 1, right? So it's just 1 out of 52. Right, so 4 plus 13 is 17. Minus 1 should be 16 out of 52. Divide by 4 is 4 out of 13. For this one, probability of a red card and then a black card. Okay. I'll just make this an R here. The red cards are half of the deck, right? If you're not specifying whether they're diamonds or hearts, then that's 13 out of 52, right? The black cards would be the other half, which should be 13 out of 52. which is, pardon me, 26, what am I saying? 26 and 26, which is ultimately 52 out of 52, which is 1, all right? That's a 100% chance, right? It's kind of a silly question, right? The probability of drawing a red card or a black card is guaranteed, all right? Because there are no green cards or anything like that. It's funny how when you're doing this, you're not really paying attention to the minutia, and then as you get into the weeds of it, you go, oh wow, what a silly question that is. The probability of a picture card and or a red card, right? And you know that these are or type of problems again, as you see this question of mutual exclusivity. Picture, so let's call this P for picture, or face if you like, and red. So R for red, if you're going to abbreviate it that way. Alright, the probability of the picture cards. There are 3 across 4 suits, right? 3 across 4. So that's 12 faces out of 52. Things that are red are, again, half of the deck. So that is 26 out of 52. And then things that are both picture cards and red. Let's see, is 3 diamonds that are picture cards that are red, and another 3 hearts. Right, so that should be 6, right? 6 out of 52. And I'm a little short on space, but if you added 12 plus 26, you should get 38. 38 minus those things that are one and the same, because they're not mutually exclusive. They can occur simultaneously. Would be 32 out of 52. So I'm going to put it up here. 32 out of 52. Wake up, please. Divide by 4. That's the GCF is 8 out of 13. Yeah, okay, so that's correct. 8 out of 13. 2. 4 out of 13. 2 out of 13, 4 out of 13, 1 whole, and 8 out of 13 for the last one. Okay. Now we're probably going to get into the multiplication rules. Alright, so let me skip over to 4 here. Yep. Sorry. For example, 4, 2 cards are to be selected with replacement. All right, red alert. You see this reference to replacement. All right, that is a signal that again you're dealing with the AND multiplication rules. Right, so we have to consider dependence or independence. Right, without replacement is dependent, meaning the second is affected by the first. Right, with replacement means one has no bearing on the other. So this is the less complicated formula, the independent type. Right. Let's try to rephrase whatever's written here. 2 cards are to be selected with replacement. So these are independent, right, from a deck of cards. All right, determine the probability that there's 2 spades that will be selected. All right, the formula would be this to generalize. probability of A and B is equal to the probability of A times the probability of B. To conform this to the conditions of the problem, if we're talking about spades, you could do this. I mean, draw a spade, and put a subscript if you want to be a mathy person, right? And then a second spade and put a second subscript. Or make one a different color, even though that's not reality, right? Yeah. But it's the probability of a spade and the probability of a spade. Right? It's doing the same thing almost exactly twice. Right? Yeah, it is exactly twice. So what's the probability of pulling a spade out of a deck of 52 cards? There are 13 spades. So it would be 13 out of 52, and then this would be exactly the same thing because you put the card back. So 13 times 13, a terrible number. You could simplify. You could use a calculator. There's no sin in that again. But if you know your multiplication tables and you're used to reducing fractions, you might go, this is 1/4, right? And this is exactly the same. So this is also 1/4. So it's really just 1 times 1 and 4 times 4, which is 1 over 16. And this is near the end of its life. Okay. Let's look at 5. Okay. For 5, 2 cards are to be selected without replacement. That means that we're dealing with things that are dependent in this case. Alright, so it's a slightly more complicated formula. Alright, from a deck of cards. Determine the probability that 2 spades will be selected in this case. Alright, so I'm just going to go for the sort of modified version of this. Alright. The probability of drawing the spade, a first spade, and then the probability of drawing a second spade is going to be the probability of the first one times, which is the multiplication formulas, the probability of drawing the second given the first occurred. Okay, remember the order in which these things are written is actually important. Okay, so we already determined from a deck of playing cards, and if you have a deck of playing cards, you could, sift through them, and you would see, that there are in fact 13 spades. So that hasn't changed. This is still 13 out of 52. But if you haven't put the card back, it says without replacement. That means that when you're considering the fraction that would represent drawing a second spade given the first occurred, the fraction has to be modified. First of all, how many cards would there be if you didn't put one back? There would be 51 for sure. But don't forget, if we're talking about spades and spades, and if this actually happened, right, that you have pulled one spade out, then how many total spades are there left over here? There would be 12 as the modification for the top. So I think you pretty much, it would be probably faster to just use a calculator, but let me see. If I simplified this to what it would be, 1/4, and then cross simplify here, 4, and that would be 3. Actually, it would work with 51, right? Yeah. $17, right? It would end up being 1/17. Yeah. Yikes. This ends up being 1 out of 17. Right? Ultimately. Right? You could just input 13 times 12 and 52 times 51. Use the ABC button and it should reduce to that. Right? I'm curious. Yeah. Okay, as you can see, 13 out of 52 times 12 out of 51 is 1/17 reduced. Okay. Alright, so pretty cool. All right. The hard part, and I remember from doing the MyLabs, like, that's the kind of thing that happens a lot, where you might go, oh yes, logically there'll be less cards total, but don't forget, if you're talking about spades and spades, and this actually happened, then that number, the numerator, essentially has to be tweaked also. Okay. Here's 6. Okay, 100 people attended a charity benefit to raise money for cancer research. 3 people in attendance will be selected at random without replacement. Okay, 3 people is important, without replacement is important. We're talking about dependent events here. Alright, so already we're going to have some example of this. The probability of A and B is going to be equal to the probability of A times the probability of B given A occurred. Alright, that's the model to borrow. 3 people in attendance will be selected at random without replacement, and each will be awarded 1 door prize. Oh boy. Are the events of selecting 3 people who will be awarded the door prize independent or dependent? It's dependent. All right. Did they actually ask you to calculate? No. I'm going to do it anyway because I think it's important. They're really only asking you whether it's dependent or independent. And if they use this phrase without replacement, you would know automatically. Now, here's the model that you would have. If you had a situation where you're talking about 3 people, you could modify this, and I think that's worthy of our time, so I'll do that. Right? So this would be the probability of A and B and C. Right, we're using the word "and" because it's in multiplication form rules. And in which case, if we're going to modify it on the right side of the formula, it would be the probability of the first thing, and since it's without replacement, it would be the probability of the second thing given A. And then there would be another factor, which should be the probability of the third thing given the first 2 things. And I have a pen on me. I want to make a little correction here. So the probability of C given A and B. Okay. If you're not putting people back in the pool, all right, then this is how it should unfold in theory. Okay. If it's 100 people, when you're randomly selecting the first person, right, it would be the probability of 1 out of 100. Right. If you're now calculating you're going to choose the second person, it would be the probability of the second person given that the first one already was taken out. So it's going to still be 1, because you're only choosing 1 at a time, out of 99. Right. And then when you get to the third person, the probability of choosing the third person given that the first 2 occurred. Because again, you're not putting them out. It's still you're choosing 1 at a time, but the pool is shrinking from 100 to 99 to 98. I don't know why they would ask you the question and not make you do the calculation, but hey, it's going to be a really puny figure. All right, because as you see, it's going to be 1 times 1 times 1 over 100 times 99 times 98, which should be something like 970,200. Let me just check. Yeah. That would be the correct denominator, 970,200. So yikes. Okay. Anyhow, you would have to use a modified version of the dependent formula for this problem. All right, let's do the last one here, example 7. And this is multiple parts here. All right. A new medicine was given to a sample of 25 of Dr. Cleary's patients with flu symptoms. Oh, what a coincidence. I have flu of some sort. Of the total, 19 patients reacted favorably, 2 reacted unfavorably, and 4 were unaffected. 3 of these patients are selected at random. Okay, this is important. 3, and there's 25 total. Determine the probability of each of the following. I'm going to have to erase a lot, so I'm going to do this down here and then unfortunately erase it immediately after. But we're going to be doing A here first. So the probability that all 3 react favorably. This is going to involve an ABC situation. And although it is not explicitly stated, it doesn't say with replacement or without replacement. I mean, one would have to assume that when you're randomly selecting people, you're not putting them back in the pool. Right? So this is going to be a dependent situation. Right? So the variety of the formula would be the probability of the first. You could use the letter A if you like. Times the probability of the second given the first times the probability of the third given the first and second. Very similar to that last problem. Okay. So, the information that is relevant, all right, about favorably, 19 patients reacted favorably, right? 19 out of 25. So we would put that here reasonably, right? If you didn't then somehow put a person back in the pool of drawing here, and I don't think you would intuitively anyhow, what would be the probability of the second person being favorable given the first already occurred, right? This is a situation where both the top figure and the bottom figure are going to be affected by this, right? Since we're considering all three reacted favorably. So for this one, it's going to be one less than 19, which is 18 logically, right? And then one less than the total because there's no longer 25, there's 24 people. All right. And then the third person, all right, if they're also a favorable candidate, a person who reacts favorably to this drug, whatever it is, that number is going to shrink further. So it's going to be 17 out of 23 right, when you multiply. So 19 times 18 times 17. You could try to pull some tricks with simplifying here and here, but you're going to get this awful figure no matter what. So I'll put the solution to this here. All right, 19 times 18 times 17, you end up with 5,814 over 13,800. This is going to be 969 out of 2,300. So in terms of a percentage, it would be something like 42%. The conditions are then going to change. Calculate the probability that the first patient reacted favorably, the second patient reacted unfavorably, and the third patient was unaffected. That's quite verbose. So to sort of make this a little bit more concise, I'm going to say it's the probability the first is favorable, and then I'll put a comma. Second unfavorable, and third unaffected. Affected. There we go. So if this is the sequence of events, are they dependent or not? I'm going to go ahead and make the assumption that it is in fact still dependent, because what's going to happen is there's not going to be replacement. All right. So whether you tweak both the numerator and the denominator as you're determining the probability for actions or not, something is going to be reduced. All right. One or the other, or both perhaps. So it helps to write out the formula as modified to meet the conditions of the problem as clearly as you can. So the probability of the first being favorable, that should be an easy fraction. All right. But if we've decided it's dependent, then it's going to be okay times, all right, the probability of the second unfavorable, all right, given first favorable, and then the probability of the third unaffected given first favorable and second unfavorable. Okay. probability of the first would be 19 out of 25 again, right? So this one is for sure 19 out of 25. Now when you consider the second one, we're not talking about a group of people that is exactly the same, right? So we want to concern ourselves with those people who are the unfavorable group, right? But given that the first was favorable, so what will shrink here is the total number of people should be 24 now. All right, but what would the numerator be? 2 react unfavorably. Since we're talking about that condition being slightly different here, 2 are unfavorable, 19 are favorable. All right, we don't have to reduce this figure. We're just going to keep 2 here. Okay. And now when we do the third one, the unaffected pool of people, the denominator will change, so it would be 23 still, all right? But in terms of the number, the unaffected people are 4. So it'd be 4 out of 23. All right. This again is a multiplication type of problem. So you could attempt to simplify first if you like, or use a calculator. What you should get in this case for B should be the outcome of 19 times 2 times 4 over 25 times 24 times 23 simplified. Right? In which case you should get 19 over 1725. Just like 1.1%, something like that. I'm beating up on my radiator here. Sorry. Okay. Alright, now I have to erase again. Okay. Now we look at C. No patients react unfavorably. Don't go to sleep, please. Okay, still dependent again. You're not going to pull these out. So the probability that none react favorably is still going to be a version of this. Right? It's going to be P of A times P of B given A times the probability of C given A and B. Okay. Now, just to modify it enough to make it a little bit easier to read, the first fraction is the probability of the first being not favorable. Now, that happens to be 2 things simultaneously, right? There's the 19, well, the favorable would be 19, but the other 2, there's the 2 that reacted unfavorably, that's not favorable, of course, and then there's the 4 that are unaffected. All right, so the probability that the first is not favorable would be the combined might of 4 and 2, right, which would be 6 out of 25 people, right? Now when you get to this one, the probability that B, which is representative of the second, given A, not favorable, right? This is a situation where the total number of people is going to be reduced logically. But if the second person is also not favorable, then the maximum of not favorable is 6, still has to shrink as well, which would make this 5 out of 24. And then a similar situation when you get the third person here. Third, not favorable. That total number shrinks, so it's 23 again. And then, because there's some similarity here, we're just still considering things that are not favorable, that number has to shrink further, so it'll be 4. So this times this times this. 6 times 5 times 4. What you should get in this case, for C, is 1 over 15. 1 over 115. One more of these. Now we go on to D here. All right. At least one patient reacts favorably. All right. Now, this is an interesting example because we could employ a formula from earlier. So let me write it out. The probability that at least one reacts favorably. We had a formula from earlier that was a derivative of the complement formula. So the probability of an event at least once is equal to 1 minus the probability of the event does not happen. Alright, so essentially subtracting from 100%, we might spare ourselves some trouble if we just calculate, that's not how you spell event, this in the context of the problem. The probability of it does not occur. Right. Why is this to our benefit? Because we just actually calculated what we need. Right. In C, it said the probability that no patient reacts favorably. So if it's the probability of at least one patient reacts favorably, or you could say the event occurs at least once, we're going to take 1 and we're going to subtract basically the solution to part C here. So that would be essentially 1 minus 1 over 115, which makes this 114 over 115, which is about a 99% chance. Okay. Okay, this again is the that version of the complement formula that is rearranged to answer the question of the probability of an event occurring at least once. Right. Okay. there's that. As I said, this is probably the best key. I would definitely print this, right, because it has all your formulas on it, and although it's, there's a lot of stuff all on one page, this is an at-a-glance. I wanted to make it that way so that you don't have to dig too much. All right, let me spare the bulb here and clean up. For homework, right, do section 11.5 in my lab, and then you're right where you need to be. And again, here is the schedule for next week, just to look at it. If I sent an email about this, but this is where we are. All right, and this is the end of next week. The final is going to be in Canvas, so you don't want any other distractions. All right, make sure that you finish these assignments by the evening of Wednesday the 15th, so that you could just have time on Thursday next week to do all of this stuff. Okay, the final, that is. All right, the more specific details of that have to be revealed to me, so I'll tell you what I know. It's going to be in my lab, is what I can tell you. This test number 3, I'm just going to give to you again as a freebie. All right, but make sure that you're doing your homework, because you really want to build up the experience in preparation for the final. Okay? All right, thank you guys for listening. I'll see you again on Thursday. All right, be careful out there.